I want to talk about derivation. Derivation part is, if someone is willing to go to see the derivation part, you can visit those lectures. Their derivation, geometry, everything is there. So that one was especially for derivation and elementary linear algebra. This class is all about application. So that's where I want to go in such situation. Okay. So today it is lecture number 2, and here in this lecture we will talk about. Hello, everyone who is not having any question, just try to mute your mic. Okay. Okay. Today it is lecture number 2, and we will talk about fundamental subspaces and decomposition of matrix. So a special decomposition that we are calling it here, singular value decomposition. I want to go much in detail that. Before that, how if someone is saying fundamental subspace, why it is fundamental name is coming? Actually, fundamental it is directly derived from the fundamental theorem of linear algebra. And there it is talking about four very special kind of subspaces and orthogonality between those two. And the singular value decomposition is highly dependent on those fundamental subspaces. So that's why title name is fundamental subspace. Coming to outline of my today's lecture. First, I would like to discuss about four fundamental subspaces of a matrix. There are actually four. One we are calling it column space, another we are calling it null space, another we are calling it row space, and fourth one is left null space. So those four fundamental subspaces we will discuss in detail, and how those things. I have taken one example. Also, I will give geometries. All these are geometrical. So that means you can visualize all these. And in second, once we are having clear idea of fundamental subspaces of a matrix, then we will try to visualize fundamental theorem. So what are the fundamental theorem? First two part are very simple. Just deal with fundamental subspaces and orthogonality. And third part of the fundamental theorem, it is talking about what? It is talking about that it will lead toward singular value decomposition. It will directly deal with eigenvector, eigenpair. I would used to say eigenvalue, eigenvector. In together, I am calling it eigenpairs. So the fundamental last part would deal with eigenpairs of a very special matrix that we are calling it A transpose A. So that kind of matrix. So that one is having meaning in singular value decomposition. And if time permit, we will go to discuss about one rank matrix that thanks to that outer product of two vectors. So how, and if you are able to, why I'm talking about that, the singular value decomposition is always talking about the representation of a matrix in the term of as a sum of finite number r number of one rank matrix. R is their rank of the matrix. So always you can decompose as any kind of matrix, any rectangular matrix, m by n matrix, into r number of one rank matrix. That one is due to singular value decomposition. And if you are having one rank matrix, that means just you are dealing with vector, and easily you can visualize eigenvalue, eigenvector of those things, and geometry is very interesting. So that those things I will discuss in one rank matrix. After that I will go to singular value decomposition. So coming to first part of this lecture, that four fundamental subspaces. So I would like to talk about here regarding a single matrix. So the four fundamental subspaces of a matrix, suppose A is a given matrix, then four fundamental subspaces of a matrix happens to be column space of A, column space of A transpose. Column space of A transpose is nothing, just how you are getting A transpose by changing column of A to row of A transpose. So just interchanging of row and column, so that things is happening. So that's why column space of A, you can call it, it is actually row space of A transpose, or simply column space of A transpose, you can say that it is a row space of A. So that criteria. Similarly, if you are having two matrices A and A transpose, then null space of A, simply we will call it null space. That means the collection of all the element which has been nullified by the matrix A. That means Ax equal to 0. All those x which map to 0. So that collection is falling in the null space. That one is a very specific interesting kind of subspace. Okay, and then left null space would come, that would happens to be a null space of A transpose. That means all those vector which has been nullified by A transpose. So there are two column space and two null space. Simply you can say that one null space of A and another null space of A transpose, two column space, one column space of A and another column space of A transpose. And column space of A transpose, also you can say that null space of sorry, column of space of row of space of A also you can say that. So they lift the understand what if why all these are saying that. I told that in linear model you always encounter this kind of situation, that means Ax equal to B, where A I will call it it is your data matrix, and B is your response vector, and X is your weight vector. So all these criteria, weight vector or parameter vector, whatever you want to say that. Generally people are sometimes calling it weight. Weight is a very general name, and parameter is a name in sense that there are two approaches to deal with modeling. One is parametric and another one is non-parametric. Parametric approach is having what we try to provide a model structure, through that we try to learn parameter. In non-parametric we don't provide parameter directly, we try to learn the function, or directly we try to learn the whatever function we are having, we try to learn the model. So that approach is coming. So non-parametric, it is a little bit tedious task you will get to know later. In if you go for higher study, then definitely you will see such kind of approaches. So those are all optimization problem. So it is, so that's where these four fundamental subspaces all are just to simplify the understanding of your solving process of a linear system Ax equal to B. Just here don't consider it is just a linear system from the linear algebra. Now onward, just you have to, every time whenever you will see that Ax equal to B, always consider this one is a linear model. It came from some structure, some model, some model structure, whether that basis, their basis might be polynomial basis 1x square, x cube, like, and like otherwise also it can be trigonometrical basis. If you are from EC, then I will also take basis from trigonometrical function as well. So there you will see that if you are taking trigonometrical basis, it is capturing more non-rigidity. Generally in signal, sound signal or speech signal, you will observe a lot of nonlinear kind of situation. So in that case what is happening, and also some periodicity also you will observe. So we know that about from Fourier series, that a periodic thing always can, every continuous function can be approximated by a Fourier series. That means what you do there, you try to express that function as a linear combination of sine and cosine with various uh, argument. Okay, so like that, in that same situation, that means their sine and cosine are playing the role of basis. So that one is capturing nonlinearity. So same thing that and if you all do all those structure and understand and putting basis thing in the design matrix or data matrix, then you finally your model will be converted into in this linear model. Ax equal to B, A would be design matrix. So all about, if you are having a very good understanding of matrix, then you can solve that. And whatever I will discuss in this class, in next tutorial I will do all those things in the Python. Okay, again, so just brush up your Python, and just definitely you might have done all that course as well. So there are several online resources, because I am having two courses already, so I am working very hard to make these courses very interesting. That's why I want get extra time to cover that Python classes. Just I will use that in linear tutorial only. Okay, so here I am talking about I will go a step wise. In a step wise, in first step I will try to find it column space of A. That column space of A, what, simply it is actually linear combination of the uh, columns of A, linear combination of the columns A of A. So A is the matrix, and Ax, if you try to visualize it more, then X is what, X will play the role of what, coefficient vector. So if you just zoom it, so that means write A like this way. A is having column, how many columns? Suppose A is the given matrix M by N matrix. So it means A is having how many columns? Who would answer? I am saying that A is given M by N matrix. That means number of rows are how many? M, and number of columns are N. So how many columns you will observe here in A? I am giving column picture. Again, I would like to say that if you want to see column picture and row picture of a matrix, go and watch that video lecture from the linear algebra classes in YouTube. Definitely, those would be very fascinating. Always try to give one picture. So column picture always looks fascinating, because from computation perspective, you will observe that column picture is giving very interesting kind of computation. So that's why I always you go for column picture. So this matrix I have just written in term of columns. So this matrix A is having n number of columns. Okay, that means n number of vector, and we know that we can do linear combination of vector in order to uh, in order to generate a space. Like if you are taking two vector 1 0 and 0 1. If you take 1 0 and 0 1, and I'm saying that find the all possible linear combination of this one 1 0 and 0 1, that means alpha times 1 0 plus beta time 0 1, where all possible, that means alpha and beta can take any real value. Alpha and beta are coming from any real value. So what would be this linear combination? Who would like to answer? What would be linear combination of 1 0 and 0 1? Anyone? What would be? Okay, Sriniketan, you just answer because you had already attended linear algebra class. Tell me, what is the linear combination of all possible linear combination of 1 0 and 0 1? Sriniketan, are you listening me? Not. I'm unable to listen you. Any other? Saurabh. Okay, fine. If you don't want to answer, because I have to proceed to class. All the vector of what? A span. A span. What a span it will give? What is the name of that a span? A space. XY plane. So in yeah, nice answer, nice. But in short, simply you can say that it is R2 now. Two-dimensional plane. Two dimension. Better name is two. There is a compact name. So directly call it two-dimensional because you are taking two vector. So two vector and a span of two vector is always a plane. That means a two-dimensional space. If you are taking three vector, then a span of three vector would be three-dimensional space. A span of four vector would be four-dimensional space. In that way, you should answer, because we are having limitation of visualizing a space. We can visualize a space up to three-dimensional only. But there in linear algebra, if you observe, we are having n-dimensional space. If you go functional analysis, there we are having infinite dimensional space. So the mathematically, that in abstract sense we need to understand those things. So through basis approach, so basis is playing very important role. So if you are having two bases, that means two-dimensional space. If you are having a single basis, that means one-dimensional space means a line, two-dimensional space means plane, three-dimensional space means a space, four-dimensional means something more than that. Four-dimensional, fifth-dimensional, those things will come. Einstein had some idea of four-dimensional by introducing time as a separate axis. He had in his theory he went for that four-dimensional space. Apart from that, no one could visualize more than four-dimensional. Okay, so you can visualize like this way. That's way if you take two bases, then you will get two-dimensional. Likewise, here we have taken n number of vector. Each column happens to be a vector, so we are having n number of vector. But what will happen among these column vector? There might be some dependency. So if you take linear combination, then effective independent linear combination or effective linear combination, it will reduce to what number of vectors, what number of dimensions reduce. It will reduce up to what number of composition, how many that how can you find the dimension of linear combination of these columns? Any idea? Up to what? Because I'm asking to find linear combination of columns, that means alpha 1 times c1 plus alpha 2 times C2 second column. If matrix is given, that means these columns are given, this column vector, you know about this column. Okay, so that's where these are known vector to you. So tell me, what would be dimension of this? What kind of a space it would be? Anyone can say that? What would be dimension? You know the answer. Just think over it, because you are having matrix and matrix is given to you, matrix is known to you. If I give a direct explicit example of matrix, then definitely you can give answer of that. But what would be dimension of this one? What would be dimension? That means what would be r to the power what? Tell me, what would be dimension of this a space generated by linear combination of columns? Anyone? Yeah, and it would be at most, you can go lesser. Yeah, n means first answer n was fine. Someone told that n, that means dimension definitely n, it could be n as well. N is the upper bound, most. So if a dimension of linear combination of this column is n, it simply says that all the columns are linearly independent. All, but suppose these are not linearly independent, there is a dependency among the columns, then definitely the dimension will decrease, and decrease up to what? Yeah, up to just it might be, it is not a smart answer, but you tried well. Any other answer? Any other? It is related with matrix. Again, I am saying the matrix is given to you. Any other answer? Just try. It is rank. It will go dimension up to rank of the matrix. So the dimension of this one would be just capital R to the power a small r. R is the rank of matrix. What is R? R is the rank of matrix. So this is the concept. So that's where column space is coming. So simply one just because you people could not understand that column space, I told several times column space. What is the dimension of column space? It is always that name of the dimension of column space is actually rank. We are calling it rank. That means rank of what? Rank of matrix. So this one is rank of matrix. Is it clear to everyone? That means in a matrix, how you can calculate rank? You can calculate rank. Several definition of rank I had given during linear algebra class. Rank can be number of linearly independent columns in a matrix. Rank can be if you are having a matrix, you can apply elimination process, Gaussian elimination process. After elimination, several round of elimination, you will see that that matrix will be converted into RREF form, row reduced echelon form, and there easily you can visualize pivot element, pivot column. So rank of a matrix happens to be number of pivot column. I'm talking all those things from computational point of view. I'm not talking from theoretical point of view. So you can do all those compute. You can compute all those things. So just keep on applying Gaussian elimination method over the matrix, and what will happen? Finally, that matrix will be converted into a row reduced echelon form, and there easily you can visualize which are the pivot column and which are the non-pivot column. So pivot column always leads to our column space, and it is giving number of pivot columns always counting rank. A non-pivot column, those are counting nullity. So that I will talk. That means dimension of null space. So that I will talk about. Those things are actually fundamental theorem of linear algebra. So simply I would like to say that if you are taking linear combination of all possible columns, then you are getting a column space, and rank of column space happens to be R. That means R is the dimension of column space happen to be rank of the matrix. So that is the theory. So this Ax, that means keep on varying all x. Then in order to vary this one, you will consider all possible combination of the column of A. Here x is variable and columns, once a matrix is given, this means what does it mean? It means column is fixed. That means C1, C2, Cn are fixed. Now we have to see the dependency, whether these columns are dependent or not. If it is not, dependent, if these are independent, simply in that case we can say that rank would be n, otherwise rank would be less than n. So there is a criteria here. In this case you can say that rank is always bounded above by n. It can't be more than n, this property. Okay, and what would be the least value of rank? What would be the least value of rank? Any idea? Least value of rank would be 1. See a scalar number. A scalar number is a 1 by 1 matrix. What is the rank of 1 by 1 matrix? So this is the, so here from column space you are getting one result. You will get another result from row space. So when we move from one combination to all combination, in that process we are getting a column space, and here x will keep on varying. We are getting a column space, and dimension of that happens to be rank of the matrix. And what does column space do? It solve a very big question, and it solve a very big problem. What it simply solve that question is coming to here, for what value of b, or what value of response vector b, non-word we will call it response vector. For what value of response vector the system can be solved analytically. That means it is having exact solution. Here solve analytically means, here I am talking about for which value of b the system is having exact solution. I am not talking about approximate solution. If we are not getting approximate exact solution, then we will look for approximate solution through that projection approach or least square method approach. So okay, so for what value? Simply it says that if b is in the column space of A, then it guarantees that the system is solvable. It is having an exact solution. Or in short, you can say that if b is in the column space of the given matrix A, then we can say that the system is consistent. That means it is having an exact solution. So that is the scenario. So someone say that if you are taking a this kind of matrix, Ax equal to 0, tell me this one is having solution, exact solution or not? Ax equal to 0, this one is homogeneous linear system. Is it having an exact solution or not? Any idea? No, it is having an exact solution. This system is always consistent. Why? The reason is that uh, column space is a space, so 0 is always contained in column space, and this zero is that means here right hand side we observe our response vector is 0, so 0 would be always a member of column space. It simply says that this system is always solvable. That means it is always having exact solution. Why? Because every subspace contains 0 element. Every subspace in linear algebra, if you take any subspace, whether it is parametric space, whether it is data space, okay, so always that will contains 0. 0 would be essentially there. So that's where this homogeneous system is always consistent. Only we have to worry about non-homogeneous part, when it is consistent, when it is this system is inconsistent. So if it is inconsistent, we have to go for least square solution or some other solution. Okay, so here question will come. That's the same question I have written here. Are the columns of A independent? In other words, does each column contribute something uh, new to subspace, that column space of A, C of A column? So if it is so contribution, so which columns will contribute? Independent column will contribute in order to construct subspace. So like if you are taking a three columns, like if I'm taking column one 3 by 3 matrix, I'm taking 3 by 3 matrix, 1 0 1 2, 1, 0, 3, 1, 1. Tell me, what is the dimension of this? What is the dimension of this column space? We are having this, call it column C1. This is the column C1. This is the column C2. This is the column C3. Okay. So what would be alpha times C1? In short, I would like to write what is the call. Suppose this is matrix is A. This is A matrix. Okay. What is the column space? Whether it would be R2, R3, or what would it be? It would be subspace of R2. What would be this one? Or simply tell me what would be dimension of this column space? What would be dimension? Any idea? Okay, here column C1 and C2 both are independent, and third column C3 is dependent on these two. That means C3 is actually sum of C1 and C2. So simply you can say that this matrix is having rank 2, and if you try to find column space, then column space of this one is a 3D, a two-dimensional plane in 3D, because here 3 dimensions column, each column having 3 components, so that's why each are member of R3. So that's why column space of this one is, it is a two-dimensional subspace in R3, or simply you can say that it is a plane in R3. The column space of this matrix is a plane in R3. That means only these two columns are significant. Third one is just a linear combination of these two. So that's why C1 and C2 are contributing in order to construct column space. C3 is not contributing. It is not. That one is ineffective. So that is the idea. Okay, going further, I will talk about another important space that we are calling it column space. So first, I would like to talk about left null space. Why? Because there is a relation between column space of A and left null space of A, that we are calling it null space of A transpose. So if we try to solve this one, uh, I will change here notation of variable. I will call it Y. So we see solution space of, we try to find solution of space of A transpose Y equal to 0. Then what would be? It is a linear combination of vectors from the domain subspace in such a way what non-pivot or independent or free variable will decide the weight of this one. Or simply, these are very complicated things. If you understand null space of a given system, then these things would be clear, and these things are you can get in those lectures. What is happening here? Here we are trying to find null space of this one. What the, null space of the system, left null space. So that means we are solving this homogeneous system, A transpose equal to 0. So just try to solve. In order to get solution, you will get a solution space. This solution space of this system, homogeneous system, we are calling it null space of the given matrix, transpose of the given matrix, or simply null space of the left null space of the given matrix. So it is null space of A transpose. Solution space of this system is actually null space of A transpose. Null, remember that it is null space of A transpose, and also we can call it is left null space of A. It is null space of A transpose and left null space of A. Those are just name. Okay, and these are very much associated with free variable. So what is happening, if you, when you are trying to solve a system of equation, there you will observe two kind of in the row reduced form you will observe two kind of variable or two kind of columns. One would be pivot column, another would be non-pivot column. So here while calculating solution space, non-pivot column, the variable associated with non-pivot column, we are calling it non-pivot variable or free variable. Those are contributing in order to get solution space. So that's why I am calling it like that. So I have taken one matrix. So I now everything would be clear. And apart from that, this matrix A may be any, it is any 3 by 3 matrix. It is a 3 by 4 matrix, 3 row and 4 column. So and this matrix, what we do, just for simplicity, we took row reduced form. You can observe that it is RREF form. So it is row reduced form. So this is the matrix. It is already in row reduced form. So here we will try to find column space of this matrix. That means all possible linear combination of the column of A and all that means solution space of A transpose Y. That means null space of A transpose. So what would be A transpose? So here you can directly calculate A transpose. That means rows of this A becomes columns of A transpose. That is the situation. So A transpose would be 4 by 3 matrix. You can, so this would come as a first column. This second row it will come as a second column, and third row would be third column of this matrix. So this situation, this is the situation. Now we are having this matrix. We will try to find column space. So what would be column space? How you can find directly? This one is already in row reduced form. Easily you can talk about what would be column space. What would be column space? Anyone? Yeah, very nice. Actually, smartly you answer after seeing the last row is 0. Yeah, yes or no? Yeah, it is nice. It is it is effectively, it is two dimensional. Effectively, it is R2. And then what would be null space? Left null space. That means null space of a transpose. It will take time because you need to solve the system A transpose Y equal to 0 and have to find the solution space. That finding null space of A transpose, it will, and that one is a time taking. It will, but remember that definitely you will calculate that. Here you already come across to see that what is what is column space, and null space easily you can calculate from there. So here null space of this A transpose, if you try to solve it, what would be? It would be this matrix would be a 4 by 3 matrix here because you transpose it. So 4 by 3 matrix. So there you will observe that 2 are pivot column, 4 by 4 by. So here two first column and second column would be pivot column in A transpose, and last column would be non-pivot column, and non-pivot column is contributing in order to calculate null space or solution space, that associated variable. So that's way I can give a picture of that null space, but that one is not. I think that one is very easy. If you watch those video lecture, it would look like very easy. If you try to solve this one directly, you will get to know. If you're solving this one, what you will get here, it becomes this row becomes column, this row becomes column, this 0 0. So easily you will get that one is very simple thing, and from there you can derive that the null space of A transpose is nothing, just it is linear combination of this z axis. It is what it is talking about, z axis. This one is talking about x axis, or simply you can say that x1 axis. This one is talking about x2 axis, and this one is talking about x3 axis. So these two are spanning our column space. You can observe here, this one is the first column, this one is the second column, and rest of columns are linear combination of these two columns. So only these two columns are linearly independent, other columns are dependent on these two dependent. So C3 and C4 are dependent on C1 and C2. So that's why dimension of column space of this matrix is 2, and the dimension of null space of A transpose, that means null, it is 1. It is just constructed by a single vector. That's why dimension would be 1. So it is linear combination of this one. So it is null space. You can easily also observe that I will talk about in fundamental theorem. You can observe something more than that. So these are column space and null space of A transpose. So this one is, and these linear combination of these two form column space of A. Linear combination of this vector will form null space of A transpose. We will go to see two more fundamental subspaces. Third one is row space. So how you will get row space? By taking linear combination of column of A transpose. Column of A transpose are what? These are actually row of A. So either you can call it linear combination of rows of A, or you simply you can call it column of A transpose. So if you try to find all possible linear combination of rows of A or simply column of A transpose, then you will get a new subspace that we are calling it row space. So and simply because here always we always feel easy to deal with columns, so that's why I'm converted it this row space as a column a space of A transpose. So just find the column space of A transpose. It is we are calling it a row space of A. So, again, how we can do that? So keep on varying this y in place of x because we are using transpose, and so that's why take it y. Just keep on varying y, then you will get complete row space. You will get complete row space, and again it is solving the same big question. If you corresponding, if you take transpose A transpose y equal to something, change it to b dash or b something like that different, so it is solving that kind of question. That means column space of A transpose. It is talking about consistency, not more than that. So just you can leave all this. Here I will talk about null space. Null space of A, the given matrix A. So null space of given matrix A is nothing, just it is solution space of the homogeneous system Ax equal to 0. So if you find solution space of this one, so that we are calling it null space of the given matrix A. So notation is simply we can call it n of A. In tutorial class we will plot all those things. Okay, so right now I'm just talking about the theoretical version. So here again the null space, again it would be decided by non-pivot columns or non-pivot free or non-pivot variable. That means the variable associated with non-pivot column, so it is contributed by that constructed by non-pivot free variable. So free variable or non-pivot variable, they are helping to construct solution space of Ax equal to 0 or simply the solution space of homogeneous equation. That means in simply we try to find all those collection of vector which has been nullified to 0 by the given matrix A. So that simply you can observe that solution space, it's saying that if you take any vector from here and apply a matrix over that, then that will be transformed to 0. So nullification of it is talking about collection of nullified element by the matrix A. So that one is coming in null space. Another name of null space we are calling it sometime it kernel space or kernel, simply kernel we are calling it kernel. Few book may use word kernel. So again I will take the same matrix example that this one is a very particular, very specific kind of 3 by 3 matrix, and what matrix I have taken it here, it is in RREF form intensely, because calculation is always simple when you are dealing with taking RREF. And one beauty with row reduced echelon form is that if you apply row reduced echelon form over a matrix, then it is not going to change the rank and independency of the columns. Rank would be invariant with respect to elementary row operation, and also what is happening, independency or dependency of column, it would be independent with respect to that elementary row operation. So that's way always whenever you are having a matrix and try to find fundamental subspaces, what you do, best way is always try to convert that into row reduced echelon form and find it out. So that is the criteria. So here we will try to find column space of A transpose or simply row space of A. Row space of A is actually nothing, just column space of A transpose, and null space of A. Both things we will find. Two things. Two we have already found got, and this one third we are trying to find row space of A and null space of A. So what are those? Here you will find. So again you need to find A transpose. We need to find A transpose. So row of A becomes columns of A. This will become first column. This will becomes second column, and 0 third row become third column. Now here we will see that this one is the first row of A transpose, this one is the second row of A transpose, and we are trying to find column space of A transpose as a row space of A. So linear combination of these two, it will give row space of A or simply column space of A transpose. You can see there, this first row and second row, it will give row space of A or simply column space of A transpose. These two will give. But again, what I would like to suggest, solve this equation in order to get null space of A. So you have to solve Ax equal to 0 in order to get null space. You will observe that it is here in the matrix itself. You can observe that how many pivot element you observe here. Pivot column, there are two pivot column, first column, second column, and two are non-pivot column, third column and fourth column. And third column is associated with the variable x3, third variable x3, and fourth column is associated with fourth variable x4. These are variable x3 and x4 are associated with third and fourth column. So that's way x3 and x4 we will call it non-pivot variable or free variable, but x1 and x2 we will call it pivot or dependent variable. Another name also we can say that free variable, also we can call it independent variable. So here x3 x4 during this solution process of system of linear equation, you might have already seen that the non-pivot or free variable, they vary freely, they can take any real value. So that's the name of those non-pivot variable happens to be free variable. They are free to vary. But here x1 x2 they are having dependency over free variable. So that's where the variable associated with pivot column we are calling those dependent variable, and the variable associated with non-pivot column we are calling it free variable. So how many free variable we observe? Two. So due to that we will get two basis vector for the column space of A, or simply solution space of Ax equal to 0. That means homogeneous. So that's why first basis is this one, second basis is this one. So these two bases in together is spanning our null space. So null space is what? Null space of this matrix is what? It is a two-dimensional plane in R4. Two-dimensional plane in R4. And what is the row space of this matrix or column space of a transpose? Again, it is two-dimensional subspace in R4. So these are the four fundamental subspaces related with the same matrix. So four fundamental. I will talk about further visualization of these in together. So visualization you can look into here. So row space and null space. That means row space means column space of A transpose. Row space of the given matrix, we are calling it column space of A transpose, and null space of A. Both are actually defined as a subspace of domain space of the given matrix. Matrix is always a linear transformation, a linear operation. So if you are taking m by n matrix, that means the matrix is defining a transformation from where to where? It is defining a transformation from Rn. Rn is the domain plane. If you are taking m by n, then matrix it would be a transformation from Rn to Rm. Rm. Okay. Likewise, so here if you are taking any vector, n-dimensional vector, and multiplying that with m by n matrix, here this one is m by n matrix. It is m by n matrix. So when multiplication is feasible, then when you are taking n-dimensional vector, then it would be feasible. So that's why this x must be n by 1 n-dimensional vector. That means column vector. That means n by 1. So m by n into n by 1. So in total, finally the right hand side you will get a matrix y. Y would be a vector, m dimensional vector, m by 1. So m dimensional. This is the situation. So here this is the row space and this is the column space. Both are actually in the domain, or we are calling it another. If you are from machine learning or data science, you can say that it is a source space. So null space of A and row space of A, or simply column space of A transpose, both are in the source space. And if you try to see column space of A and null space of A transpose, then both would be in target space or response space, or you can say that output space, or you can say that there are various names, or various name you can say, as much as name you want you can give it. So target space, response space, output space, there are various names. So null space of A transpose both would be in the target space. Better name, common name, better you should use target space, or you can say that codomain also. It is null space of a transpose. Both would be here. So that is the scenario of four fundamental subspaces geometry. Now I will go to discuss about fundamental theorems. If time, okay, we don't have time. Regarding attendance, in other next class we will cover this fundamental theorem. Regarding attendance, go and mark your attendance there in the Google Classroom. Okay.